Are there questions?
When you study the gauge transformation of how T mu changes.
Yes.
What is delta T mu? How are you defining it? Is it T prime mu evaluated as x minus T mu evaluated as x?
Yeah. So we assign all transformation laws to delta T. We first calculate T prime mu of x minus T mu of x, right? And the background you say is the same, right? So that change is what you are assigned to delta T.
I was getting some minus sign.
You're getting some minus sign.
When you calculate delta T.
Yes. Okay. Yeah, I think that you can just change xi to minus xi. Maybe that's just a convention. Yeah.
That is only some part of the Einstein equation. So I got all the complete Einstein equations that you.
No, that is only the scalar part of the Einstein equation, right? Then there will be vector part and then the tensor part. But those will only affect the vector fields, the vector modes and the tensor modes, right? So as far as the scalar modes are concerned, these are all the equations that you have to deal with. Right? So 4 equations, and as you saw, we have 6 variables. So you have to do something to, we have to put some additional condition on the table. Okay, thank you. Thank you. Okay, so if there are no other questions, I'll begin. So as we just said that we encountered a situation where we have 4 equations for 6 variables, right? So now we are going to discuss what kind of condition we want to put on the T mu nu, okay, so as to reduce the number of variables to 4 so that we can go about solving it. Okay. So the first postulate that we'll be taking is the perfect fluid postulate. So this says that T mu nu locally will have the form E of x, G mu nu of x plus E of x plus rho of x u mu of x u mu of x. So here p and rho are arbitrary functions and u mu is an arbitrary vector which can depend on x. Okay. And we also impose one condition, okay, but that condition of course can be can be relaxed by changing rho. Okay, so we use that g mu nu of x, u mu of x, u mu of x is -1. So the only content of this condition is a minus sign, right? Because this 1 can always be changed by simply multiplying u of x by some function f of x, right? And that function will just change the definition of rho of x from here. Okay, but the minus sign is important. Okay, so u mu is a time-like vector, right? That's what we are assuming. So now let me discuss what it means physically, right? Why, I mean, what does this assumption translate to from physical viewpoint? And for that, it will be easiest to go to the local inertial frame. So take a given point x naught. Okay, some space-time point x naught. So at this point, we can go to a local inertial frame. Such that g mu nu of x naught is eta mu nu. Right? That's the definition of a local inertial frame, and the first derivative of g is 0. So in this local inertial frame, u mu will go to some vector. But we had seen in the GR course that even after you have demanded this, right, you are still left with some additional coordinate transformation at x naught, and that is Lorentz rotation. Right? You can make a Lorentz transformation, okay, at x naught. Right? That doesn't change either of these conditions. So using that Lorentz transformation, we can bring u mu to the form where u mu of x naught is just 1 0 0 0. Okay, just go to a boosted frame in which u mu is purely time-like. Is that clear? Because this condition has to be satisfied, right? Eta mu nu, u mu has to be -1, but we can take it to a purely time-like. So in this frame, let's look at the form of the energy momentum tensor. So in this frame, we have P mu nu, T00 is P minus P, because G00 is eta 00, which is -1, plus P plus rho times 1 times 1, right? Because U0 is 1, so that's rho. Okay? P I0 is 0 because G I0 is this is eta I0, right? That is 0. And here it's UI U0, UI is 0. Right? P I0 is 0. And P Ij, this doesn't contribute because UI and UJ are 0. This gives you P times delta Ij. Yes.
Is it always possible to find some coordinate where the fluid always getting moving?
Yeah, that's what it's not at every point. That you can go to a coordinate system in which the fluid is at rest at x naught at any given space-time point. In a different space-time point, you have to change your coordinate system.
I see. But if I'm able to find some coordinate where there exists some fluid which is at rest at all times,
Yes.
what we do when we do the analysis of how radiation will decay and how matter will decay.
Yeah, because that is homogeneous and isotropic universe. Yes, exactly. Right?
That's only possible in a homogeneous.
Exactly. Right. And now we are studying fluctuation. Right. So what we are saying is that when you take into account fluctuation, right, it is not possible to go to a coordinate system where a single coordinate system where the universe is homogeneous and isotropic. Right? But nevertheless, locally you should be able to find a coordinate system in which it looks like the ordinary fluid, right, with some pressure and some energy density, and that's what this is capturing. Right? Conversely, you can say that if this is true for every space-time point, right, then you can always go back to a general coordinate system and it should have a structure like this. Right? So this structure of the energy momentum tensor basically is equivalent to demanding that at any point in space-time, you should be able to find a coordinate system in which the energy momentum tensor looks like the standard energy momentum tensor of a fluid at rest.
The energy momentum tensor that you have written are all at x naught only, right? It's not away from x naught, right?
This is a general postulate.
No, I'm talking about the right column. I mean, T00 equal to rho.
at x naught. Sorry, somebody had a question? Okay, okay. Yeah, so these are all at x naught. Okay. So we'll take this as a postulate, right? That we'll assume that the energy momentum tensor has this form. Is that clear? Okay. So the fluctuations are parameterized by P, rho, and U. Right? Fluctuations in P, rho, and U. Because this is a parameter, this is the parameterization we have chosen for the energy momentum tensor. Okay. But before we study fluctuations, let's determine the background values. Background values. In FLRW. So FLRW, the metric is minus dt square plus lambda of t square x square. This is the background value of the metric. T00 is T bar 00 is rho, T bar ij is P bar lambda t square delta ij, and T bar I0 is 0. That we will try to see what choice of U and P and rho satisfy this. So you can easily check that this corresponds to P equal to P bar, rho equal to rho bar, and U mu equal to 1000.
So assuming that perfect fluid form.
Yes, we are just trying to take this perfect fluid form and see what it means for the background. Right? Now, the fact that the background has P equal to P bar, rho equal to rho bar is not surprising. That's the way we had parameterized it. Right? But the extra thing that we learned is that in that background corresponds to U mu being equal to 1000. Is that clear? So one of the consequences of this is that Ui is purely fluctuation. Okay. And U0, okay, so U0 satisfies U0 square minus U square times G, sorry. Now you're considering the fluctuating metric. So we have this condition that G00 U0 square minus Gij Ui Uj plus okay, this all everything is plus Gij Ui Uj equal to minus 1. Sorry, Gi0. Okay, this is the condition you have to satisfy. Okay. So from this we see that this is quadratic in fluctuation, right? So you don't worry about that. This is also quadratic in fluctuation because Gi0 is pure fluctuation, Ui is pure fluctuation, right? This is also quadratic in fluctuation. Okay. So we can write this as G00 U0 square is minus 1, okay, or U0 is minus of G00 to the power half. Minus.
I think Gi0 is also linear in fluctuation.
Yes, Gi0 is also linear in fluctuation. right? Ui is linear in fluctuation, so these are all quadratic. Okay. So this gives you u0 equal to minus g00 to the minus half. Right? G00 I had already parameterized, right? So there is nothing to parameterize there. Okay. So u0 doesn't capture any new fluctuation. Right? U0 is already determined in terms of the fluctuations that I already introduced. Right? So new fluctuations come from the ui's, okay, and then fluctuation in p and rho. Okay. So fluctuations are parameterized now by fluctuations parameterized by p tilde, which is p minus p bar, rho tilde, which is rho minus rho bar, and ui. Here, okay. So in this part, we are trying to determine what u was in the background. U mu, right? And what we determined is that u mu was 1000 in the background, right? And p was p bar and rho was rho bar.
This is the FLRW result from F.
Yes, FLRW background, right?
We are matching with that and comparing.
Exactly, we are matching with this form. Okay, and so the standard FLRW, whatever the energy momentum tensor you have, right? That corresponds. So the statement is that the energy momentum tensor of FLRW corresponds to u being chosen as 1000. Right? Because if you take u to be 1000, then t bar 00 is rho. Right? T bar ij is this because this part doesn't contribute. Ui is 0, right? For 1000. So it just gets this contribution. And t bar I0 is 0, right? Because again, the u component, the spatial component doesn't contribute, right? And this is exactly the FLRW background. Okay? You can also go in reverse, right? We know that this is true, right? Compare this with what you have there, and you will conclude that this is, let me call it u bar. Right? You will conclude that u bar has only 0 component, which is 1, and all the spatial components are 0. Right? Essentially, if you want to set t bar I0 equal to 0, right? T bar I0 you can see gets contribution proportional to ui u0, right? Okay. So that basically ensures that all the ui's are 0 in the background. And once we have understood that all the ui's are 0 in the background, right, then that means the ui is purely fluctuation. Right? That is the net content that we borrowed from here, that ui is purely fluctuation. Okay? And u0 has no independent fluctuation, right? Because u0 fluctuation is determined by the metric fluctuation that you have already determined. Okay? So ultimately, these are the parameters that parameterize the fluctuation of t. Is this clear? And now we can compare it with what we had earlier. P tilde and rho tilde are exactly fluctuations of p and rho that we introduced earlier, right? So ui, okay, we remember that we parameters ti0 as qi, right? We are introducing fluctuation qi of t, right, which is via this ti0, and tij we are introduced as p times gij plus sigma ij.
I have one question.
Sorry, t, yeah. Go ahead.
So in the so perfect fluid is kind of a restricted kind of manner, right? So the degrees of freedom that a perfect fluid has will be much less than the degrees of
Exactly.
freedom followed by t.
Exactly. And you are trying to see what are the degrees of that means some of the degrees of freedom would have been set to 0, right? We are just trying to see what degrees of freedom we have lost. Is that clear? So ti0 was qi, tij was had this form, and t00 was minus rho, right? This is what we had. Yeah, okay. P plus P bar plus P tilde. Yeah, okay. Let me write it that way. This was P bar plus P tilde delta ij plus sigma ij. And T00 was minus rho bar plus rho tilde, right? So let's compare it with this. So T mu nu in that parameterization would be P times delta mu nu, because we are raising G mu nu, new index up, right? That's delta mu nu, plus P plus rho u mu u nu. Is clear? So just compare. Oh, Ti0 I didn't write. Ti0. Okay, so from here Ti0 will be. Okay, so this is what we had earlier. Let me put them in a box. This is what we had earlier. This is the new parameterization, right? This is a new parameterization that we are introducing. This is what we had earlier, right? And you have to compare that. So first, let's look at the Ti0 comparison, right? This is Qi, right? And here Ti0, this doesn't contribute, right? And this contributes P plus rho times Ui u0. Okay, so Ui is already a fluctuation, right? So everywhere else we can put it, replace it by background. So this can be written as P bar plus rho bar times background. So this tells us that Ui is what we called Qi earlier over P bar plus rho bar, and U background is 1. U0 background is 1. Right? So this tells us how to identify Ui with what we had earlier. U0 you have already identified. U0 has no independent degree of freedom, right? Okay, in terms of earlier fluctuation you have identified, and then I'll leave it as an exercise. That P is P plus P bar plus P tilde, and rho is rho bar plus rho tilde. Okay, those you can get by comparing the other components, T00 component and Pij component, right? What we're calling P and rho here, right, are basically in this language, it's P bar plus P tilde and rho bar plus rho tilde. Pardon?
This was our definition in the.
In this, okay, maybe forget about the fact that we had introduced a P. Otherwise, I should have introduced some P prime there, right? P prime and rho prime, because that's a priori that's a different parameterization compared to what we had yesterday, right? And we are trying to compare these two parameterizations, right? So yesterday, yes, indeed, we called it P and P bar rho bar, but just remove this line, right? You think of this as a parameterization that we had introduced yesterday. This one.
What was the constraint on sigma? Was it traceless transverse or only traceless?
Yeah. We had the condition on sigma was traceless and no transverseness. Sigma, then we decompose sigma into several parts. right?
So perfect fluid has no sigma.
Perfect fluid has no sigma. So sigma ij is 0.
But in terms of fluid, sigma has both shear and rotation.
Yeah, sigma has a scalar part and a vector part and a tensor part. All three are set equal to 0. Yeah, so sigma ij equal to 0 basically means all three are set equal to 0.
But I'm just a bit confused about this rotation. So the terms which come in right on the equation.
Yes.
The shear and rotation.
Yes.
So there is a relation. Shear is stressless transverse, I think, and
Yes.
rotation is antisymmetric. And
Yeah, rotation of, okay, sigma is symmetric,
sigma is symmetric,
right? Because that we saw, because it's a part of the metric fluctuation, right? So sigma is symmetric. So from that point of view, sigma, so it's a defined it's a symmetric tensor that you are decomposing, right? Okay, is this okay? Are there other questions? Okay. Sigma ij equal to 0 because Tij, if you calculate, right? This part is not there. Uj is quadratic already, right? So this part is not there. Everything is proportional to delta mu nu, delta ij, right? And that basically shows, comparing with this, that only this part is non-zero.
This is supposed to be an extra condition we needed, right? Like,
This is an extra condition that you are imposing. That the energy momentum tensor has this perfect fluid form, right?
what condition is it giving me now?
It's giving you these two conditions. Okay, this is just a definition of UI. It's not giving any condition. But sigma ij equal to 0 is a condition that it is giving.
Okay, that's what.
Right? In yesterday's parameter, I said completely general. We had used a general sigma ij. Right? Now this is telling us that sigma ij has to be is equal to 0. If the fluid has this part, if the energy momentum tensor has a perfect fluid form, then sigma ij is set equal to 0. And sigma ij equal to 0 basically means that all components of sigma ij are 0. So sigma ij equal to 0 implies that sigma tilde is 0, sigma I is 0, and sigma ij is 0. For scalar that we are currently studying, this is a relevant equation. Right? These will come in the vector and the tensor equation. Right? For the scalar, this is a relevant equation. Okay. So this gives you eliminates one variable, right? But we had two extra variables, right? We had 4 equations, 6 unknowns, right? So you have to make a further postulate to eliminate the another variable. Okay. And that postulate we take is the following: okay, that if P equal to F rho is the equation of state, we use for FLRW, then P bar plus P tilde is equal to F of rho bar plus rho tilde. Which means that the equation of state of that the fluid satisfies, right, is the same as the average equation of state that we use for FLRW, right? But of course, there is locally there is fluctuation because rho fluctuates, right? So the fluctuation in P is controlled by the fluctuation in rho, right? But the functional relationship between remains the same.
Local isentropy assumption.
Exactly. The fact that the only variation, right, is because local fluctuation in the temperature, and the temperature determines both rho and P, right? Which, I mean, if you eliminate the temperature, then it's like if we write rho as P as a function of rho, is the same function that controls things everywhere. Is this clear?
So one question I had. So when we write the perfect fluid form for the stress tensor, I mean, aren't we making some assumption about the equation of state?
No, at that stage, you didn't make any assumption about equation of state, right? Because P and rho we kept completely arbitrary, right?
Okay.
Now we are making a statement about the relationship between P and rho.
Okay.
At that point, P and rho could have been completely independent functions.
Okay.
Okay, so now we expand it out, right? This I can write as f of rho bar plus f prime of rho bar times rho tilde. Okay, second order term we ignore. And then of course P bar is equal to f of rho bar. So this tells us that P tilde is equal to f prime of rho bar times rho tilde. Okay. And this has the following consequence. Okay, so you have to we translate it into the gauge invariant variable. That PE, we call the definition of PE. PE is P tilde minus this I can write as P tilde minus, see P bar and rho bar are related by this functional relation, right? P bar is equal to f of rho bar. So and now the del T of rho bar cancels. So this is P tilde minus f prime of rho bar times rho tilde. And this is equal to 0 by this condition over here. That P tilde is f prime of rho bar times rho tilde. Is this clear? Okay. So these assumptions, right? I mean, these are assumptions, but they are well motivated, right? Because the kind of fluid you expect during the expansion of the universe do satisfy these assumptions. Right? That's why we are allowed to use this. Okay. And so this basically sets two of the gauge invariant variables to 0. Sigma tilde is already gauge invariant, and P is a gauge invariant combination that we constructed. So P is also 0. Okay. So now out of those 6 variables, we have set for 2 of the variables to 0. What here? Oh, I used the fact that P bar is a function of rho bar. Just use chain rule of differentiation, right?
This P bar equal to for macro particles, just P bar is equal to 0.
P bar equal to 0.
Otherwise, it's some rho by
Exactly. Yeah.
And fluctuation also follow the same.
Exactly. So the idea is that for the fluctuation should also follow the same equation, same relation, right? But that doesn't mean that locally in a given coordinate system, those things are 0, right? Because there is motion, right? So it's only in the local inertial frame, right, where u mu has been set equal to 0, right? Then this equation follows.
Why that's a local setting? This order for without any local.
Yeah, no, this is true. But what I'm saying is that when you say the pressure is 0, right, doesn't mean that the Tij is 0, right? Because Tij can also get contribution because the fluid as a whole is moving, right? So that is all I'm saying, that you have to keep that into mind. That in mind. That
Okay, that UV part is set to 0 only in the local.
exactly, right? Only when the UV part is the UI part is set equal to 0, right? Then this that you can interpret this by saying that the Ij component is 0. Well, not zero, but is isotropic. Right? So basically the fluctuations we are thinking of as this fluid moving locally, right? And the temperature of the fluid fluctuating locally. Right? So locally the fluid is moving and it has different temperatures at different points. Right? So that's the physical picture that you are using for the stress tensor. Okay, so let me write the equations that we are going to use. Okay, we had already written the equations, but we'll now write it and remove the extra terms that we had there. So the first equation was 3H yes.
This equation is there an equation of state which is obeyed by the inflaton fluctuation? Does that obey this?
Well, there approximately P is equal to minus rho.
The background, that's true.
Background, it is true, right?
But this, we're saying things even about the fluctuation. That the equation of state is maintained.
Yeah. The perfect fluid form is maintained by scalar field. That you can check. Because scalar field energy momentum tensor, right? T mu nu has a part that is proportional to G mu nu and a part that is proportional to del mu phi, right? So using that, we can identify what u mu is, right? Using that, and then locally, yes, so you can probably write these are the condition between phi dot, as long as phi dot is approximately constant, right? That's what you assume, right? The change in phi dot is small, right? Then the P over rho ratio remains all approximately constant, right? V plus phi dot square over V minus phi dot square.
So in some slower approximation, my inflaton is a perfect.
That's right, yeah. Okay, but the point is in the, I mean, we don't need to apply this during inflation, because there you have already studied the equations exactly, right? Without in the form by taking the energy momentum tensor in the scalar field form, right? And you have seen that the phi b and psi b are 0, and then the r and xi, right? Oh, sorry, r goes to a constant, right? Okay, so that we know as long as the inflationary phase is there, that will continue to hold, right? So the place where we really need is after inflation ends.
And perfect fluid does not. So this the fact that equation of state exists for my fluid. There is one more. Assumption.
Yes, there is one more assumption, exactly, right? Because the fact that the P can be expressed in terms of rho, right? It depends on what other data you have, right? If you have a lot of data in the field, right, then the rho is not the only variable, right? But in this case, I mean, as long as it's a slow roll, right? P is approximately equal to minus rho, and if you have a non-zero phi dot, right, which is small, then P over rho has that ratio of V minus half phi dot square over V plus half phi dot square. Right, you saw that in the expression for P and rho, one had a plus sign, one had a minus sign, right? So as long as that ratio is constant, P over rho ratio remains fixed. But we don't really need this, right? Because you are not going to apply this, because for the scalar field, we have explicitly solved the equations, right? We can use those solutions, right? This is needed only when the scalar field has gone, right? When you can no longer describe it as a scalar field fluctuation by the scalar field dynamics.
So in the bigger evolves in some manner,
Yes.
and then inflation stops.
Yes.
And then this kind of matter will start dominating the dynamics.
Exactly. Because the inflator, whatever energy was there in the inflaton, gets converted to this kind of matter. Right? Because the phi starts oscillating around its minimum, right? Then that energy gets converted to other standard model particles. So once you exit the horizon, right, then this dynamics, not even once you exit the horizon, once you exit the horizon or once the inflation has stopped, right? Because inflation may continue for a while after you have exited the horizon. Because if you look at this picture, right? I mean, in horizon exit may be here for sufficiently long wavelength modes, right? Inflation still continues up to this, right? So up to this, we can use the same equations that we had derived, right? Which basically is a trivial statement that R becomes constant, right? Phi b and psi b are 0 and R is constant, right? So whatever R was here, it remains constant, right? So the worry is how to evolve it from there to here, right? And that's what we are going to study.
Why are you saying R is R meaning VC scalar or the?
No, that's the curly R that I introduced.
So why is constant inflation still happening, right? So
Yeah, but we saw that it goes to a constant, right? That if you take a pure de Sitter, right? In pure de Sitter, R approaches a constant.
Okay, I don't think I understand this. Why would I?
Because we solve the equations, we looked at the 2-point function,
Yes.
and if you remember, as tau goes to 0, right, it went to a constant,
Okay, that's true.
right?
The 2-point function went to some constant.
Yeah, so which means that the 2-point function, I mean, okay, if we apply the Klein-Gordon operator or whatever the differential operator on this 2-point function, right? There is that main term is the one which is acting on the first function, right? Okay. So the equation of motion also makes it constant. If we just solve the equation, see the equation of motion that 2-point function satisfies, right, is basically a single particle equation of motion. Right? 2-point function also has additional singularity of the source. Right? Otherwise, it is a single particle equation of motion. As a consequence of the single particle equation of motion, it actually goes to a constant. I mean, you can explicitly solve the equation also, right? If because it's exactly the same mathematics, right?
Okay.
Yeah. So the issue is that after this, okay, how to evolve it? Okay, so let me write the equations, then we'll see where the simplification occurs. So this one, I'm now going to set equal to 0. Right? Because sigma tilde is 0. So this is where the first place where we actually use what we learned. And then we had the I dot, which is minus h. Pi was given by minus h. So this one I'm going to replace by minus pi. Okay, because p is 0. Okay, so these are the two places where the equations will simplify once we put the condition on the energy momentum tensor that we derived. Okay, now we have to study initial conditions. So first of all, so this is all at T star. Right, this is, well, I just erase that figure. For every mode, we have different T star, right, depending on the value of K, because this T star is when this corresponds to when omega inverse or mod K inverse, mod K is equal to lambda H. Okay, and because H is changing slowly, okay, this T star depends on the mode, the K. Okay, so initial condition on T star. So let's so R. Okay, this is what we had defined R as. So the idea is that we have to now re-express this in terms of the inflationary data. Okay, and then see what it was. Phi and psi have the same interpretation because they are the same fluctuations of the metric that we had during inflation and now, right? The only difference is that this rho bar, p bar, q tilde, right? These are general, right? You have to evaluate them during inflation. So during inflation, rho bar was p of phi bar plus half phi bar dot square. With this calculation we had done yesterday, but I think we had used the wrong sign. Let me do it again. Q tilde is Ti0, right? Q tilde comes from, so Ti0 we had parameterized as the derivative of Q tilde plus Qi.
First sign is equal to
Pardon?
the sign given half pi dot square minus.
Oh, yeah, thank you. Minus plus.
So what is about gauging the
No, these are the equations. Yeah, so everything is written in terms of gauge invariant variables, right? So phi b, psi b, zeta, and r, right? So let me write the list the variables because there are too many things. Zeta, r, phi b, psi b. These are the gauge invariant variables, right? Because p and sigma tilde have been set equal to 0. And these are the equations for these four variables.
Why are these equations second order in time derivative?
Oh, because in Einstein's equation, it always happens that you can eliminate the second order and make it first order. No? Because like FRW, for example, right? You could eliminate the second derivative. So all those manipulations have gone in here. Right? After doing all those manipulations, it's written in terms of this first order derivatives. Okay, so now Yeah, so we are trying to now find the initial conditions for all these variables, right? And we said that initial condition on phi b and psi b are just 0. So phi b at t star is 0 and psi b at t star is equal to 0. Right? We are seeing that their correlation functions are all 0. Right? So no fluctuation of phi and psi at t star. So you have to figure out what r is and what zeta is at during inflation, right? That's what we are trying to do now. So r involves all these, right? So I have written the p bar and rho bar, and t now I am going to identify what q tilde is, right? Q tilde, we know what it is in a general evolution. We have to now evaluate it during inflation, right? Because then we can figure out what q tilde was at the time of inflation, right? At the horizon exit. So q tilde was introduced by this. Ti0 was del I q tilde plus qi, capital Qi. Right? Capital Q has no divergence. But during inflation, this is given by
Please explain this, why we took is equal to 0, 5 8.
oh, because during inflation, we had calculated, if you remember, the 2-point function of phi b, psi b, etc. And we said that all of those are 0.
Yeah.
Right? The only fluctuation was in the r. Right? We introduced this. Okay, that r is not necessarily this r. It will turn out to be the same r, but that r. So we had introduced 3 variables during inflation, 3 gauge invariant scalars, phi b, psi b, and then r, and only fluctuation was in the r fluctuation, right? Okay, that's why phi b and psi b we are setting equal to 0. So this I can write, okay, since I'm working to first order in fluctuation, here I have to pick the background. Okay, and here, okay, background doesn't depend on the space coordinate. So for del I phi, I have to pick the fluctuation. So this is minus why minus? Because you have to lower the index. The 0 index you have to lower from above, right? And that lowering can be done with the background metric. So G00 is just -1 in the background. So it's minus this. So this tells us that Q tilde is, this is phi tilde. And Qi is 0. Because this is pure gradient, right? It can be written as a gradient of phi tilde del 0 phi bar, right? So capital Qi is 0, small q tilde is minus phi tilde del 0 phi bar. Is that clear? So with this I can calculate R at inflation during inflation is psi plus H over rho bar plus P bar is phi bar dot square. And then, okay, this minus became plus because of this minus sign. Phi tilde phi bar dot. So this is psi plus H over phi bar dot times phi tilde. And now if you look at your notes, this is exactly the same, what we call R. During the okay, so this initial condition on R is basically set equal to what we had during inflation, R star, right? So we say that R equal to R star, T star. Okay, this is the one calculated from inflation.
Why are we doing it at T star? I thought we want to evolve after the point where inflation has ended.
Yeah, but during this part, right, as I said, R remains constant anyway from the equation of motion. During inflationary equation of motion, right, if you look at that, then because of this tau, as tau goes to 0, right, that is the late time, it goes to a constant, right? So as I said, this was, we did it for the 2-point function, but if you just study the classical equations, you will find exactly the same solution, because the 2-point function after all was constructed from the classical solution, right? So you will find the classical, as a classical solution, it just goes to a constant. So that's how we evaluate at T star, right? And we will see also explicitly here that R will indeed remain constant, right? At least during this phase.
So because its 2-point function goes to 0.
Yes.
We know that it's a constant in space, but here the argument requires that it be constant in time. The R. Right? Because we're saying from
No, 2-point function goes to 0 as tau goes to 0, which is t goes to infinity.
Yes.
Right? So because it goes to
tau goes to infinity is the end of inflation, right? Where this
yeah, exactly. Tau goes to infinity is the end of inflation, right? So, but the actual quantity that comes, right, is this k square over h square tau square, right?
Yes.
Okay, so tau goes to 0 doesn't mean that you have to take all the way tau to 0, right? As long as the k square over h square tau square becomes small,
Yes.
you can ignore that term,
Yes.
right? And then it becomes a constant. Sorry, k square over h square tau square becomes large. See, because there is one, so there is a term factor of 1 plus 1 over k square tau square, right? Omega square tau square. And then there is tau square sitting outside. Okay. So what we need is that omega tau should become large. Is that what I? No, omega tau should become small. Omega tau much less than 1. Right? As long as omega tau is much less than 1, right? This tau square will this will dominate. This tau square will cancel, and it becomes a constant.
Yes. And this is the RK prime correlate.
This is RK prime correlated, or you can also think of this as an equation of motion for R.
Yes.
Right? It will have the same dependence. Right? Because this factor actually came from the solving the equation of motion. Right? So it will have the same dependence. And what we will find is that this omega tau becomes much less than, as when this becomes much less than 1, right, this factor just goes to a constant. Right? So omega tau much less than 1 is like essentially this region. Right? Because omega tau equal to 1 is this one. Right? T star. So once t has passed T star, right, that means this factor has become smaller than 1, and it has gone to a constant.
Is there also some requirement of omega that?
Yeah, omega is this one. This line is controlled by omega inverse, right?
Right, but this approximation we're doing, for instance, there can be some omega can be so small.
Yes.
The line is way above.
Yes.
And there this approximation just does not work.
Well, the point way above meaning if the inflation hasn't even started, then of course it will not happen.
But
What?
let's say inflation has started, but the omega, but the length scale is just very large. So omega inverse is very large.
Yeah, very large means very slow wavelength, right? I think that shouldn't matter. Low wavelength, this would always work.
I'm trying to understand above which frequency I'm supposed to look at.
I think as long as inflation has started and you can use slow roll, right? You can continue to use this formula.
Because here I'm seeing that that 1 by omega square has to dominate tau square.
Yes, exactly. Yeah. So small omega is okay. Small omega means large length scale. Right.
But it also says that omega can only be as small as 1 by T star.
No. T star is not a fixed object, right? It's given omega, I determine T star. Right? So if omega is here, T star will be later. Right? So omega determines T star.
Okay,
So because that's the way we calculate, for example, the spectral index, right? That omega determines T star, right? And then that T star, I mean the H and V, etc., everything has a small dependence on T star because it's slow roll. Right? That's why the spectral index is non-zero, right? Because things do change slowly as a function of omega. Is it okay? Okay, so now we have to also calculate zeta, right? That's the only thing that is left. So minus zeta is psi plus H okay, these are the definition of minus zeta. And you have to convert this into phi. Okay, because during inflation we use the variable phi tilde. We didn't have rho tilde and rho tilde separately. So now we use the fact that rho is approximately V of phi.
The camera is not moving online.
Or maybe just send a message to the AV team. It's moving now? Okay. Okay. So rho is approximately V phi bar, right? Then there's of course the phi bar dot square that we use there. Right? But here it's enough to keep the V phi bar, right? Because you are always keeping the leading term, right? I mean, here the reason that you have to keep this is because when you added rho bar and P bar, right? This leading part got cancelled. Okay, but otherwise we can just use this. So then this one is given by V prime phi bar times phi bar dot and rho tilde. So rho, right, this is rho bar. This is also rho bar. Rho bar plus rho tilde should be equal to V of phi bar plus phi tilde, which is V of phi bar plus V prime of phi bar phi tilde. Right? So you see that rho tilde is V prime of phi bar times phi tilde. So minus zeta plus psi plus H over these are all phi bars. So this is the same as that. Right? So zeta, initial condition on zeta is the same as Ri. Right? Because during inflation we didn't have these two independent variables, zeta and R. Right? And if you remember, I had written that R equal to minus zeta, right? That is in anticipation of the fact that after the inflation, you have exited inflation, right? Zeta and R are independent variables. Okay. During inflation, zeta and R were the same, or minus zeta and R were the same. Okay, so we set zeta equal to Ri, R star, sorry, minus R star at T star. So let me add these two here, or I can just add those initial conditions here. So phi b equal to psi b equal to 0 at T star. R equal to R star and zeta equal to minus R star at T star. Okay, so these equations together with those initial conditions, now we can use to evolve the fluctuations. Is it okay? Okay, so now we are going to discuss an approximation, right? Because as we saw, as I had said, that as long as your super horizon, that means as long as omega inverse or mod k inverse is larger than lambda inverse h inverse, we expect the equations to simplify, right? Because the microscopic physics shouldn't affect the evolution, right? We are now going to see that how it follows from these equations. Okay, what does it mean to have small omega, right? Small omega is super horizon, right? Omega inverse is larger than the horizon size. So we see that for small omega, right, or small k, the terms that involve k square are small, right? Take for example the expression for pi. You have k square over lambda square h square, right? This is small for super horizon. So these terms we can ignore. Similarly here it doesn't, the h doesn't quite appear, but the correct way to interpret this, right, is that you divide by h square, right? This becomes h inverse psi b dot, right? That's the that means how much psi b changes during one horizon size, right? That's what one Hubble expansion, right? That's a natural parameter. Then this also becomes k square over lambda square h square, right? So this term also you can ignore. So super horizon evolution allows us to set this equal to 0 and pi equal to 0. Okay, so we are going to first solve the equations super horizon, and we will see that things simplify a lot.
The super horizon is before this exiting.
No, after exiting. Right? Super horizon means the actual size, length scale of fluctuation is larger than the horizon size. Right? The horizon size is what I have plotted in this curve, right? The horizon size is changing like this, moving horizon size, right? And we are assuming that omega inverse is larger than that, right? As long as it stays above this curve, right? So for the kind of omega, right, for which the perturbation remains super horizon all the way to last scattering, right? These equations will suffice. If I just solve with k equal to 0, that is enough. Right? For equations which enter the horizon, right, for which for example, suppose the last scattering surface is here, right? Then it remains super horizon up to this point, but after this, it becomes sub horizon. Right? So after this time, those terms become important. Okay, and you have to take those into account. Is this point clear? So super horizon evolution. That means k small, k square over lambda square h square is much less than 1. So ignore k square terms. So this immediately tells us that pi is 0. Right? Pi is 0. So xi dot is 0. Zeta naught is 0. So zeta is constant. So zeta remains equal to minus r of t star all through the super horizon evolution. Right? As long as the perturbation remains super horizon, okay, zeta is set equal to minus of r star all through.
Just saying what this corresponds to super horizon. We are taking
Yeah.
k square to be small, which means
Super horizon basically means that as long as for the time scale, for the period of time for which this line remains above this curve,
okay.
right? Forget about the last scattering, right? That is defined. Whether it entered before or after last scattering is a separate issue, right? These equations setting k square equal to 0 will remain valid as long as this line stays above this curve. Right? That is the meaning of super horizon. Right? So for this particular thing, it will hold up to this point. Right? Then it's a separate issue as to whether the last scattering time is before or after this. Right? But as just a abstract mathematical principle, you can say that the solutions that you are finding, we making this approximation, will hold up to this point. Right? After that, zeta dot is no longer 0, so zeta will start fluctuating. Right? Because pi is not 0. Pi you cannot ignore this term. Is this clear?
All this gauging where 4 gauging varying quantities we have now.
Yes.
That is describing all this varying field.
Yes.
So once the universe enter into this super horizon epoch, that time there is no communication will be happening between the fluctuations because the horizon scale is smaller than that of the fluctuation.
Yeah, but we will not need to use it. I mean, all this is already contained in this equation, right?
That's why this, for example, the zeta is just remains constant.
Exactly. That's right.
Communication cycle.
Exactly. But not everything will remain constant. We will see that some things will change, right? But their equations will be simple. Okay, now the next thing we want to do is to eliminate this time derivative part from these two. Right? So 1 minus 3h times 2. I should note that this psi b equal to phi b always holds, right? So you don't really have phi b as independent variable, right? We can just set phi b equal to psi b. That doesn't require even super horizon, right? As long as sigma tilde is 0, psi b is phi b. So you really have 3 variables and 3 equations. Okay, this equation is trivial. Okay, so once you eliminate that, then what happens? And this term we are ignoring, right? So that basically means that this should be equal to 3h times this. Right? This one should be equal to 3h times this, right? That's what this is saying. So this implies that 4 pi g, okay, let me read out from my notes. Equal to
Yeah, the camera is not moving again.
okay, hopefully it will start moving. Is it moving? Okay. Is it okay? So 4 pi g gets cancelled on both sides. H in the denominator also you can cancel. So you have to find the expression for rho bar dot, but this is of course the background rho bar, right? So if you can use the whatever you have learned earlier, right? We have this equation, remember, the ddt of rho bar lambda cube is minus 3 p bar lambda square lambda dot. So this tells us, gives us rho bar dot lambda cube plus 3 lambda square lambda dot times rho bar is equal to minus 3 p bar lambda square lambda dot. So rho bar dot is minus 3 p bar plus rho bar lambda square lambda dot over lambda cube. Okay. But this quantity is basically h, right? Which is lambda dot over lambda. So we learned that rho bar dot is minus 3 p bar plus rho bar times h. Is fine. So this tells us that minus 3h rho bar plus p bar times zeta plus psi b is equal to 3h rho bar plus p bar times r minus psi b. Okay. So psi b part basically gets cancelled from both sides. Right? This factor you can first cancel. So this basically tells us that r is minus psi, minus theta.
How did we get ddt of rho bar lambda cube versus
Oh, this was part of the FRW. When we studied the FRW, this is the energy conservation equation. Right? We had this rho, the lambda dot over lambda square equal to 8 pi g over 3 times rho bar, right? That was the one equation. The other equation was the energy conservation equation. Right? This is what tells us, for example, that for matter, the rho falls off as 1 over lambda cube. For radiation, it goes as 1 over lambda cube and so on, right? It's that formula basically.
This comes from conservation of T mu, right?
T mu, exactly. Right? This is conservation of the background T mu in the FRW. D mu T mu equal to 0. Is clear? Okay. So zeta we have already seen is constant. Right? So this tells us that r is also equal to constant. So conclusion, zeta equal to minus r star, r equal to r star, and phi b equal to psi b during super horizon evolution. Sub horizon basically will require us to take into account these terms, right? And that we'll see that that's what will produce the oscillation, right? That we had indicated, right? But right now we are just doing super horizon, right? So the solutions are simple. There's no oscillation anywhere so far, right? And we'll see that the final equation also doesn't have any oscillation. Okay. So we have determined all this. So now all it requires is to determine psi b, right? Okay. So you can use this equation because one linear combination of these two we have already used, right? So you can use this one. This is the only remaining one. This one we have used. This one we have used. That is the only remaining equation. So we get psi b dot plus h psi b equal to 4 pi g rho bar plus p bar by h r minus psi b. So I'm going to write this as all the psi b's I will take on one side plus h plus 4 pi g over h rho bar plus p bar psi b equal to rho bar plus p bar over h r. Now, in any given era, we can find out what rho bar and what the time dependence of rho bar and p bar is. Okay, and just solve it. Okay, so we'll do that after the end. Just
Shouldn't there be a 4 pi g on the right hand side?
pi g on the right hand side. Thank you. So what is going to happen? Okay, this is what I'll discuss, that in any given era, right, you use this. Any given era means when it's a matter dominated, radiation dominated, etc. This will behave like a damping term, and that basically will dampen out psi b dot, right? Psi b will always go to a constant at the end. Okay, if you use p equal to w rho, right, psi b will go to a constant. So use p equal to w rho. So result is that psi b goes to a constant. Okay, the psi b dot goes to 0. If we accept this, right, then we can figure out what this constant is, right? So let's do that. Okay, and then maybe next time we'll try to solve this in more explicit terms. So if psi b dot is 0, then we can solve this as psi b is equal to 4 pi g rho bar plus p bar over h divided by h plus 4 pi g over h rho bar plus p bar times r. Right, I just ignored this 1 plus h plus. I just ignored this term, and then that just gives a solution for psi b as a ratio. Okay. But let's just make sure that it actually goes to a constant. Right? Otherwise, this whole procedure will not be valid. Right? It's only if it goes to a constant, then it's self-consistent at least. So this I can write as 4 pi g rho bar plus p bar over h square plus 4 pi g rho bar plus p bar. R of course is constant. Okay. Now we use the fact that h square is 8 pi g over 3 times rho bar. So this then gives you, so the 4 pi g basically cancels rho bar plus p bar over 2/3 rho bar plus rho bar plus p bar times r. And now if you use p bar is equal to w rho bar, we see that this is 1 plus w over 2/3 plus 1 plus w r. That's 3 times 1 plus w over 5 plus 3w. R. So first of all, psi b doesn't go to, it doesn't remain 0, even though it started from 0. Right? It doesn't remain 0, it's driven by r. Okay, it's driven by this. During inflation, it was 0 because w was -1 there. Right? So that's why psi b was 0. But once you exit inflation, right, and once w, the equation of state start differing, then psi b starts changing. Okay. Furthermore, you can see that this result doesn't depend on initial condition. Right? The initial condition is in the transient part, right? That just gets damped out. Okay? And you get just a constant that depends on only the equation of state and that era, right? So in radiation dominated area, it will take one value, right? Where w is equal to 1/3, right? I think it's what, half probably, right? Yeah, 4 divided by 8. In radiation dominated area, it will be like half, right? In matter dominated area, w is equal to 0, so it's 3/5. So psi b changes from era to era, right? But what happens is that in any given era, it approaches a constant. Then once it starts getting dominated by something else, it changes and then again approaches a constant and so on. So this makes it easy to use this formula because last scattering happened during matter domination, right? So if we want to know what psi b is at the time of last scattering, okay, we just use the value of r is we know because that's constant, right? That has been running from the inflation. Okay? Take the value of r and multiply by 3/5. If you want to know what it was in the radiation dominated area, you multiply by half. Is this clear?
So last scattering in that diagram
Is somewhere here, yeah. Somewhere here. Yes, it's from there. Exactly. Right? That's why you are interested in knowing what the fluctuations were at the time of last scattering. Right? After that, what happened? That doesn't affect CMB. Okay, so next time we will actually solve this and show that it really approaches this constant. Right? But once you accept that, once you assume that it approaches the constant, then you can get the value of the constant without doing any calculation, right? Without solving any differential equation. Right? Otherwise, you have to solve this first order differential equation.
in principle, if somebody could see this from CMB, I don't know, this is a super horizon mode, right? So
yeah.
So this lies above somewhere.
Above 2 degrees. Basically, in terms of the angle in the sky, above 2-degree fluctuation is the is what we can say. I mean, in that fluctuation, you just use this formula. Right? Below 2 degree is the scale where that's the scale where it's here, right? So in this region, you can apply that formula, but after this, you have to change the formula, change the evolution.
I see. And this constant, this is a constant in the sky also. This R, but which is what constant. So constant,
it's constant. Okay, it's constant as a function of time, but of course, you are seeing it at a given time slice, right?
No, but sorry, I thought in a given era, it's something.
It's constant. R is always constant. R is constant all through, right? It's a phi b or psi b,
Right.
that is constant only in a given era, and it changes in another era.
I see. Psi and R are both gauge invariant.
Yeah, all of them are gauge invariant. So you are only using gauge invariant variable here. Right? Everything is gauge invariant. Right? Later on, when you try to make connection to what you observe, that it will be useful to fix a gauge. But at this stage, you have not fixed any gauge.
So in principle, it's possible to observe both from the last scattering era right now.
Yeah, I mean actual delta t over t, right, will involve a combination of the two. Yeah, you are asking whether it is in principle possible to calculate observe individually and compare these 3/5 whether you can see, right? I don't know if there is a way to do that.
But in principle, it should be, right?
In principle, yeah, because these are independent fluctuations, right? All of these are gauge invariant. So in principle, if you could do, I mean, very, very fine experiments, maybe all of these you should observe separately.
And the function which we want to determine by looking at CMB, that function is going to be R star or some combination of R star and psi.
Exactly. It will be a function of omega, right? What you want to determine is what you know from CMB is how things depend on omega, right? Or K.
Right.
So it will be eventually determined by all of these fluctuations. Right? But because these fluctuations depend on K, right? The size of the fluctuation, that's what you can compare with the experiment. Right? The low K are the super horizon modes. They never entered, they didn't enter the horizon before last scattering. Right? The high K, right, which are the high L, will be the sub horizon, which are the modes which have actually entered the sub horizon region. Yeah, so in principle, I think because these are all gauge invariant, if you could do sufficient number of observations, right, you should be able to see all of these.
So delta T by T, you're saying measures one combination of R and psi.
It will involve all of these, right? Basically, all the gauge invariant, it will be some combination of all the gauge invariant objects that will be measured by delta T over T.
And then tensor correlations will also.
Yeah, tensor correlations will directly measure the HH 2-point function, right? The HT 2-point function that we determined,
Yes.
right? There again, I mean, what you will see is that as long as you are super horizon, those fluctuations are exactly what you got at the exit from inflation, right? Things are constant.
But those correlations will not correspond to some extra degree of freedom. These degrees of freedom.
No. Those are extra because these are all scalar degrees of freedom, right? HH correlation will be the tensor degrees of freedom, tensor modes, right? So we'll see that those can be observed in principle by looking at the polarization correlation, right? Those will affect the polarizations of the CMB, right? So if you could do calculate the correlation between polarizations, that puts the bound on the HH, the tensor modes. And the vector modes are not there, right? Vector modes get damped out, and it is first of all not there during inflation anyway. And what we'll see is even if they are there, that they get dampened out very quickly. Right? So the vector modes are not there, but scalar modes are there and the tensor modes.
You said that R will remain constant.
R will remain constant because xi dot is 0, right?
Psi dot is 0
Because pi is 0, this is we are K is false, right? So xi dot is 0, and we also saw that R is equal to minus xi. R is equal to minus, then again that's a consequence of this combination of these two equations, right? 1 and 2. If we assume that K is 0, see all of these fail when K is non-zero. You have to redo the analysis, right? As long as K, we can ignore the order K term. Right? R is equal to minus xi, and xi is constant, so R is also constant. And the value of the constant is what you had at the inflation exit.
So we assume some perfect fluid and fluctuation on top of it, and it looks like that sources scalar fluctuations in the geometry, in metric.
Yes.
Is it not possible that I have some kind of quantum field during inflation which sources even the tensor modes in the metric?
Well, the H in a sense sources the tensor modes in the metric, right? Yeah.
H is the tensor.
Is the tensor mode. H is the metric modes, right?
Yes.
The metric fluctuation.
Yes. So
Okay.
that itself is the tensor mode. But
That's the tensor mode.
Equation that is sourced by something
You are saying if there is some other scalar, other fields. Yeah, it has to be a massless field and it has to have participate in the dynamics sufficiently, right? Because otherwise, what would happen there is if it's like a normal radiation, it will just get dampened out, right? But if there is genuinely massless field, then yes, indeed it could have an effect. Right? I mean, for example, if the inflaton consists of two fields instead of one, two light fields, say, right? Each of them will fluctuate in general, right? And then you have to study what happens in that case, right? Take into account the effect of mixing and so on. Right? This is the simplest case where we assume there is only one scalar mode and use that to study this. But this part of the analysis is independent of that, right? What will happen is the initial conditions will now be different, right? If you use a different model of inflation, right, you will get a different initial conditions. Okay, but these variables are the same variables that you have to use, right? Because these are the most general variables in FLRW, right? That you just assume arbitrary generic form of the stress tensor. So the two parts of the calculation, one is this part, right? In fact, this was done much before inflation, right? This evolution of perturbation, right? Without knowing what produced those perturbations, right? And then inflation gives you a origin of what produces a perturbation.
All these things that we talked about today, ignoring that k square by lambda square.
Yes.
That with respect to CMB, that's like more than 2 degree fluctuations.
Yes, more than 2 degree, exactly.
And
Right? Now, this will be also useful for fluctuations of less than 2 degree, because for fluctuations of less than 2 degree is this case, right? So up to this point, these equations are valid, right? So after this point, this part of the evolution, we have to take those into account. Okay, so I think we'll continue tomorrow. Not tomorrow, next week.
I'm having some trouble in understanding these fluctuations in the CMB.
Okay.
So there is overall more than 2 degree range. There are some